Hello student, in this video we will study about the refraction of light part 2. In part 1 we studied regarding the refraction of light, refractive index and we solved few questions based on refractive index. I will suggest first you go through that video. So here what is a spherical lens or transparent material bound by two surfaces. So here these two surfaces could be plane or spherical, means it could be one surface could be plane or other surface could be spherical like this. So this is called as plano concave. Similarly, if we have another lens, one is plane and the second is convex, so it is called as plano convex. But for CBSE 10th grade, we have to study only the lenses where the both surfaces are spherical. So here we can consider both the surfaces as spherical. So it could be convex lens or it could be concave lens. If I zoom it, here you notice at the center, convex lens is more thicker than the edges. Means when we are moving towards the center, thickness increases. But reverse happens in the concave lens. In concave lens, at the center, it is thin. But when we are going away from the center, means towards the edge, we notice that its thickness increases. So that's why convex lens is bulging outward. You can say convex lens or double convex lens. Both are similar thing because in both the side we are using a convex lens. Similarly, this is double concave lens. So let's talk about both of the lenses. Convex lens are bulging outward. It is thicker at the middle as compared to the edge. So that's why convex lenses are converging in nature. Similarly, if we talk about concave lens, concave lenses are bulging inward. It is thicker at the edges than the middle, and they are diverging in nature. I explained more about the converging and diverging concept in Reflection of Light Part 2. But here also I will try to explain regarding the converging and diverging property. Our next topic is terms used in the spherical lenses. So first term is optical center. The central point of the lens. If we have concave and convex lens, so the center point of the lens is called as optical center and it is represented as O. Next is center of curvature. So what happened if we have a convex lens? So here in convex lens, we have two transparent surfaces. If I name it as surface 1 and here is a surface 2. So based on these two surfaces, we have two spheres. With respect to one, our sphere is, with respect to one, the sphere could be in this way. And with respect to two, the sphere could be this. So the center of these two spheres is called as center of curvature. So based on 1 and 2, we can say that this is C2 and this is C1. So we can define the center of curvature when the transparent surfaces forms a sphere. The center of a sphere is called as the center of curvature. It is represented as C1 and C2. If we take a concave lens, this is our surface first and this is the surface second. If we make a sphere, so this is C1 and this is C2. I hope you understood this point properly. Next is principal axis. Principal axis is defined as an imaginary line which passes through the two center of curvature. Means an imaginary line which passes through C1 and C2. And if we make one point C1, another point C2, so the line that passing through C1 and C2 is our principal axis. Same way for the concave lens, if this is a C1 and this is C2, so here is our principal axis. Next term is aperture. The effective diameter of the circular outline of a spherical lens. Means if we see a convex lens, so it has certain diameter. This diameter is called as aperture. Next is principal focus. So as we have two center of curvature, so similarly we have two principal focus. If we take a convex lens and we draw a principal axis, this is our optical center. Here it is C1, this is C2. So what happens if we take any incident ray? Suppose we are taking from the left side. So what will happen? It will converge and it will pass through the principal axis. So the point at which the refracted ray touching the principal axis is called as principal focus. Similarly, if our incident ray is on the right side, so then where it will go? It will refract and moves in this way. So here, this is another focus. So for lenses, we have two principal focus. If the incident ray is on the left side, focus is on the right side. If the incident ray is on the right side, focus is on the left side. So that's why left one we can mark it as F1 and the right one we can mark it as F2. So principal focus is defined as when the incident ray passes through the spherical surfaces the refracted ray will pass through the principal axis. And the point is called as principal focus. So this principal focus lies between the optical center and the radius of curvature. So here one thing we can note it down. We consider the incident ray on the left side. So for convex lens focal principal focus is considered principal focus is f2. But for concave lens principal focus is f1. So here if we take a concave lens, here is the C1, this is C2. So as I told you, we are considering incident ray in the left side. So what will happen? Here is the incident ray. So concave lens is diverging in nature. So it will go away. So if we keep the track of the refracted ray, it will pass through this way. So where the refracted ray is meeting on the principal axis, which is represented as principal focus, which is f1. So for concave lens, our principal focus is f1, and for convex lens, our principal focus is f2. This we have to remember because in sign convention, we will use this relation. Next term, focal length. So focal length is the distance between the principal focus and the optical center. So if we draw a convex lens, here is our C1, F1, F2 and C2, and this is our optical center. So if we take the incident ray, so what will happen? Convex lens is converging in nature, so it will pass through F2. So focal length for the convex lens is the distance between optical center and the focus. So here this is the F. Don't take the left side as the focal length because incident ray is on the left side, so its refracted ray will be on the right side. Similarly, if we draw a concave lens, this is our optical center. Here is the F1, C1, F2, C2. So if we take the incident ray, it will diverge in nature, and then its refracted ray will trace the path. So in concave lens, focal length is on the left side. So here we can summarize. For convex lens, focal length is on the right side, and for the concave lens, focal length is on the left side. As we know that focus lies between the center of curvature and the optical center. So we know that the distance between principal focus and optical center is focal length. So it means that center of curvature and the optical center will be 2 times of the focal length. So that's why this C1 and C2 is also represented as 2f1 and 2f2. Now we will study about the rules of image formation in the spherical lenses. Rule number 1. When the incident ray are parallel to the principal axis, the incident ray will always passes through the focus. This rule is similar to the reflection of rule image formation. So for convex lens, optical center f2, c2, f1, c1. If we take the incident ray, it will converge and passes through f2. Similarly, if we take a concave lens and if we take the incident ray, left side, it will diverge and refracted ray will pass through the focus. So previously I already mentioned that principal focus for the convex lens is f2 and for the concave lens is f1. This you have to keep in mind. Next, move to the second rule. Second rule is the converse of the first rule. It says that when the incident ray passes through the focus, it touches the surface and gets refracted. The refracted ray is parallel to the principal axis. So this is our convex lens. If we take the incident ray which passes through f1, if we take the in, if we take the if we take the incident ray which passes through the f1, so after touching the surface it gets refracted and become parallel to the principal axis. Same way for the concave lens. This is our incident ray. This is our incident ray. Which could pass through the This is our incident ray. This is our incident ray, which is passing through the focus F2. Then it become parallel to the principal axis. So this is our rule number 2. Let's move to the rule number 3. When the incident ray passes through the optical center, no refraction of light takes place. It means that the light will pass straight without bending. So in rule number 3, we take an example. Let's take a convex lens. And here is the incident ray which passes through the optical center. So this incident ray will move straight without bending. So why it happens? So if I zoom it, what happened in this case? If I see this region, so what do you notice? This is the incident ray and this is the surface. So if we try to make a normal over this surface, the normal and the incident ray both lies on the same path. So here incident ray and normal both coincide. So that's why it will pass without bending. In part 1, I explained this part in a proper way, so you can check this out. Similarly, if we draw the incident ray in the concave lens, so if we take the incident ray passing through the optical center, it will move straight without bending. So these three rules we will use in the image formation of the spherical lenses. So let's study about the image formation in the spherical lenses. So here in image formation of a spherical lenses, first we will discuss regarding the convex lenses. So in convex lens, there are total 6 positions of the object. First is when the object is at infinity. Second is when the object is beyond 2f1. Third is when the object is at 2f1. Fourth is when the object is between 2f1 and f1. Fifth is when the object is at f1. And the sixth is when the object is between f1 and o. So there are total 6 positions of the object. One by one, we will draw the image formation of each of the position of the object. Let's start with the first one, when the object is at infinity. So when the object is at infinity, it means that incident ray is parallel to to the principal axis. So here is our convex lens, and if we consider the incident ray which is parallel to the principal axis, so we always take the two incident ray. So here both the incident rays are parallel. So according to rule number 1, when the incident ray is parallel to the principal axis, it always passes through the focus. And for the convex lens, focus is f2. So as you see, image is formed at f2 and it is highly diminished. So we can write the nature of the image. First is, it is real and inverted. So in the lenses, when the image is on the right side of the object, then it will form the real and inverted. Second is, it is highly diminished. And third is, image is formed at f2. Similarly, we will go for the second position of the object, which is beyond 2f1. So we will draw a convex lens. I always draw the ray diagram so you get better concept regarding the image formation of the spherical lenses. So if we take the object beyond 2f1, and we always have to take two incident ray. So first we can take the parallel. So in concave lens, parallel always passes through f2. And second we consider through the optical center. So image is formed between f2 and 2f2. If this is AB, this is A dash, B dash. And it is on the right side of the object. So it means that it is real and inverted. And one more thing you can notice, it is diminished. So here, the nature of image is it is real and inverted. Second, it is diminished. And the third is image is formed between f1 and 2f1. Sorry, f2 and 2f2. So this is the image formation beyond 2f1. Next is at 2f1. So we can draw the convex lens. Here is the object at 2f1. We can consider two incident ray. One is parallel to the principal axis. So it will pass through f2. And second through the optical center. So if this is the object AB, so if this is the object AB and here image is A dash, B dash. So in this case, image is real and inverted because image is on the right side of the object. Second, the size of image is equal to the size of object. And the third, it is formed at 2f2. So we can write the nature of the image. First is real and inverted. Second is image size is same as object. And the third is image formed at 2f2. So I hope you understood this image formation at 2f1. Let's move to the next one, which is between 2f1 and f1. So let's draw the convex lens. Here the object is present between f1 and 2f1. Let's take the two incident ray. One is parallel, so it will pass through the f2. And second, we can take the optical center. So if this is our object position AB, so image is formed at A1 and B1. And image is beyond 2f2. And it is real and inverted because image is formed on the right side of the object. And it looks like it is magnified. Nature of image. First is real and inverted. Second, magnified. And third, image is formed beyond 2f2. So this is the nature of image between 2f1 and f1. Next is when the object is at f1. Let's draw a convex lens. Object is present at f1. So here is the object at f1. So we take the two incident ray. One is parallel. So parallel always passes through f2. And second, we can take through the optical center. So here both the refracted ray are parallel to each other. Both are parallel to each other. So we assume that when the incident ray or refracted ray are parallel to each other, they will meet at a point. So that point is present at infinity. And because the point is at infinity, so the image size will be highly magnified. And the image is on the right side, so it is real and inverted. So we can write the nature of the image. So first is real and inverted. Second is highly magnified. Third is image will form at infinity. So these are the first five image formation of a convex lens. Before we go to the sixth one, which is between f1 and O, I want to summarize these five image formation. So what happened? Object is at infinity, then the image is formed at focus, which is at f2. Second, when the object is at f1, that time image is at infinity. Means basically it becomes reversed. When the object is at infinity, image is at focus, And when the object is at focus, image is at infinity. Third, when the object is beyond 2f1, that time image is between 2f2 and f2. If we place the object between 2f2 and f1 and f2, that time image is formed beyond 2f2. So object when it is at 2f, image is between 2f and f, and when the object is between 2f and f, that time image is beyond 2f. This is also reverse. And the last one, which is the fifth condition, where the object is at 2f1, that time image is at 2f2. This is the one of the part. Second is, what about the size? When we are going from infinity to the optical center, then the size of object decreases. Size of object decreases. In reverse, you can say that size of image increases. Means when we are going towards the optical center, object size starts decreasing. But the image size, which is going away from the optical center towards the infinity, that time size increases when it is moving from optical center to infinity. And at which point both are equal? Both are equal at 2f1. Means at center of curvature, the size of image and the size of object both are equal. But when the object is moving towards the optical center, that time image will go away from the optical center and the size of the image will start increasing. So I hope you understood this summary. It will help you to understand this image formation. Now we can move to the last image formation, which is between f1 and O. So let's draw the convex lens. Object is between O and f1. So here is the object. We can name it as AB. One of the incident rays parallel to the principal axis, so it will pass through the focus. Second, through the optical center. So what will happen? The distance between both the rays starts increasing. It means that they are diverging in nature. So if any ray which will diverge, it means that it must have certain starting point. Like in this case, if we have these two rays are diverging, it means that it must have a starting point. So similarly, here, if the refracted ray are diverging, it means that they must have certain starting point. And this starting point is magnified. This starting point is magnified. We can name it as A dash, B dash. So what is the nature of image? First, it is virtual and erect, because the image and object both are in the same side. Second, it is magnified. And third, the image is formed behind the object, or you can say that image is formed same side as object. So that's it in the image formation of the convex lens. Now we will move to the image formation in the concave lens. In the concave lens, there are two positions of the object. First is at infinity, and the second is between infinity and optical center. So let's move to the first position of the object of concave lens, which is at infinity. Let's draw the concave lens. So as we know, when the object is at infinity, it means that incident ray is parallel to the principal axis. So let's take the two incident ray, both are parallel to the principal axis. We know that concave lenses are diverging in nature. So here both the rays meeting at the point F1, and it is highly diminished. And the position of the image is on the same side as the object. So it means that it is virtual and erect. So here is the nature of image. First is virtual and erect. Second is highly diminished. And the third is image is formed at F1. Let's move to the second position of the object. First we will draw the concave lens. Here object can be placed anywhere between infinity and the optical center. So if we place the object at this point, we take a incident ray parallel. So concave lens is diverging, so it will go away and passes through F1. Similarly, if we take another ray which will pass through the optical center, so as you see, if I zoom it, object is at A, B. Here is the image form. This is A dash, B dash. So the nature of image is virtual and erect because it is formed on the same side of the object. Second, it is diminished. And third, image is formed between F1 and optical center. So this condition is applied for anywhere object is present between O and infinity. So the nature of image is virtual and erect. Second, diminished. And third, image formed between F1 and O. So that's it in the image formation of the spherical mirror. So here we have studied about the image formation in the spherical lenses. In the next video, we will see the sign conventions and the lens formulas, and we will also solve few problems based on it. I hope you understood this video, and if you understood this, please subscribe the button so you will get updates regarding more videos. Thank you.